Yeah. So welcome everybody. And what I want to do first is to give you a kind of introduction to the course and the kind of layout and so on, and where you find the information and everything. And after the lecture, we will have the first lab session just to get started with the project. And it's going to essentially be more paper and pencil in the beginning. And Alexander is going to be one of the TAs. So he'll be at the lab here. So we have this room here till 2 o'clock. So it's going to be a long day. So we do the lectures in the first 2 hours, and then we have the lab thereafter. So this is very much a project-based course. And you find all information on the official website of the university. And that's also where you find the schedule and all the basic information. And for those of you who are not familiar with the University of Oslo system, if you go to schedule, you can also subscribe to updates on the schedule. So you can get either a text or an email in case there are changes. So the schedule is also, if you peep into it, is also the place where I will put the recording. So you will find a link to the recording of the lectures. So those of you who have followed the courses which I've been teaching, you've already seen this setup. And if you scroll down, you will find the weekly messages, which I put up here. I will send an email with updates and plans for the week. So you will typically get through Canvas an email every week with the updates, etc., etc. But roughly this is where you find information. And then you have a similar information on Canvas, which we will use for communications and also for assignments and handing in the projects. I guess you're pretty familiar with that, right? Is everybody here familiar with the UIO system? Okay, you have not been at UIO before. Okay, so this is the official web page. And if you look at the information down here, you will see that all the teaching material is actually available from the GitHub address. And if you go to the GitHub address, this is actually where you find everything. And there you will find a little bit of basic description, a little bit list of softwares, computational tools, etc., which you will find useful. So the question is, what kind of programming language you're planning to use? So I just need to say that in the lectures, I will often use Python because that allows me to visualize immediately. So in the lectures, I will often switch between whiteboard, the PDF slides, or the Jupyter Notebook when I'm running codes. So this is roughly going to be the kind of setting. And that does not mean that you can use other programming languages. So we have the templates in C++, but we also have a template for the projects in Python. If you want to do a program in Fortran, let me know. And I know that some people want to experiment with Julia. Is anyone who wants to experiment with Julia? We have another language which people have been using, which is called Rust. Does anyone want to study that one? Feel free. But we can guide you in C++, Python, Fortran, and Julia. These are the programming languages which I have been using. So if somebody's a Fortran aficionado, let me know, because that was my first programming. No, actually, my first programming language was BASIC and then Pascal. Okay. That means that I come from archaeological times when it comes to computing. Okay, so this contains a lot of the basic information and where you also find textbooks, but I'm going to repeat some of these things for you. This is where you find everything, and you can, if you're not familiar with Git, and which is a version control software, or GitHub, we are not going to teach that, but we will help you in the lab sessions. And with Git as a version control software and GitHub, which is just a provider, it's actually owned by Microsoft, which gives you access to a repository, you can then clone everything down. Either if you have installed a GitHub desktop, you will have the same with GitLab. You can use Bitbucket or whatever if you are using a version control. We strongly recommend using version control software. So I always like to tell the story of, well, it's a very sad story because I had a student who didn't use version control and was writing on the thesis and had 3 months of thesis work and was on the train, went to the restroom, came back, and somebody had stolen the laptop on the train. And 3 months of work were just gone. If you then use version control software, you can do continuous updates of your files. You can always use the history option in Git and GitHub, and then reconstruct the file which you had at a certain day. So if you had a program which is working, and then you made some changes, and it doesn't give you the right results, and you cannot figure out, you can always go back to a previous version. So version control is something which makes life very, very simple. And I strongly recommend it as a tool. There is another tool which I recommend strongly, which we will not teach, but which I would like to teach as a course. And this is about, so if you go to, I'm going to send this as a link to you. I have it as a link on the course on machine learning, which I teach. And this is AI Agents for Science. So this is a course which is just brilliant. And I strongly recommend it. It increases your creativity, your efficiency. If you're working with your thesis, this is a fantastic way, especially if you develop large software packages. Take a look at these slides. I'm going to send the link to you later. Strongly recommend it. And we actually encourage you to use these kind of tools in this course as well, especially when you're developing large numerical projects, which this course is actually about. It's not cheating. This is actually the way you work efficiently as a scientist nowadays. Actually, this course is excellent. I would have liked to teach that one. Doesn't mean that you shouldn't attend this course, right? Okay, so what I want to do now is to quickly go to the slides, and I'm going to show you some of the basic things, which we are going to go and discuss through the semester here. And so let me just bring this up. And I just wanted to say a little bit about the layout and the kind of projects which we are going to deal with. So today we are going to look at the introduction to the course and overview topics. I will also try to sneak in the first project, which we will do all together. But then this forms the basis for the next projects or alternative projects. And this depends very much on your research directions. So I like to portray these courses as a kind of paper writing courses, in the sense that some of the projects can become scientific articles. So this has happened in previous years. It's not a requirement, but it's something which can lay the foundation for things of interest for your thesis work, etc., etc. So the basics here is Monte Carlo methods, but Monte Carlo methods for solving quantum mechanical systems. So that's the first project, and that's the first half of the semester. Then the second half depends a little bit on your interests. See, as you can see, we will always use Zoom for the lectures. So in case you cannot be here, you can always attend via Zoom. Secondly, the lectures will be recorded, so you can always look them up again. So you have the links here. These are the slides where you can find them, either as a Jupyter notebook. If you replace the Jupyter notebook shorthand here, you can, with PDF, you have the PDF slides, which I'm watching now. There are 2 code templates, because most of the people here have tended to choose either C++ or Python as programming languages. So let me ask you, how many of you plan to write codes in Python? Yeah? C++? Okay. So we have the 2 templates here, which you can start looking at for writing the codes. But as I said, in the lectures, because I often visualize results and I run shorter calculations, then I typically use Python. But you can easily translate that. Actually, Anthropic's Claude or ChatGPT do this job for you. So I should say one thing when we discuss these things. I strongly encourage you to use these tools. It makes life much easier. But the kind of doing the basics is something which is very important, because having understood the basics and done the basic coding means that you can say whether what these softwares provide, these large language models, is correct or not. So at a certain point, you have a tool which is great. It simplifies many things. I do use them efficiently, so which often saves me a lot of time because I know what I want to do. And sometimes if I were to write the code, it would take me 2 to 3 weeks to do that, even longer time. And then I get a skeleton, a framework, and then I can look from that skeleton whether this is meaningful or not. And that gives me a lot of the kind of simpler things which would have taken me a lot of time to write and which saves me time. And then I can use my creativity on other types of problems. And these are kind of tools which you should not feel intimidated using them. It's actually extremely helpful. And so in a certain sense, we provide you here with 2 templates, which hopefully can aid you in working with the projects. And the idea is that this first project is going to be a lookalike of what we might call a professional research-ready Monte Carlo code for doing quantum mechanics. So that's roughly the goal for the first project. And yeah, these are the people involved. I have a textbook which I will, 2 textbooks. So one is out of print and you can actually find it on this Google Drive. The other one is this by Sandro Sorel and Federico Pesca, which is a very good textbooks, which you can download for free if you are at the University of Oslo with a UIO student account or an employee. As long as you have a UIO identity, you can go to the university library and you can download this for free. Okay, so you don't need to pay for it. And I will, in the lectures, I will often refer to sections or chapters which are relevant reading backgrounds for that specific week. So this is roughly the schedule, and the deadlines here. These are again for your planning of the semester. So in case you have problems with the deadlines, we can always tweak them a little bit, but they are meant for you to plan the rest of the semester. And we want you to write these reports like scientific articles. That gives also people a good training in preparing yourself for, let's say, the master thesis, the final master thesis project, or if you're doing your PhD, it gives you, and you have not written a scientific article before, or paper, or report, then this is something which can be of help. This is roughly the outline. So we have these 2 compulsory projects. They count 1/2 each. And this is roughly the kind of programming backgrounds which we can offer. So I have long experience in Fortran. This is what I used when I started writing larger numerical projects. And then the similar with C++. C++ is a very complex language. It's a very rich language. And sometimes it can be difficult to actually use the full potential of C++ because it's such a rich language. And that's why large language models can often give you hints. So when I write a code, I typically ask, can you improve the code for me? Or bring in additional things which I may have overseen. Because it's such a rich language that it's almost impossible for many of us to actually have the full view of all the possibilities. So what we want to is to be able to apply central many-particle methods. So I know that some of you are familiar with many-body physics. So how many of you have taken a course? I know that 2 of you have taken a course in many-body physics. How many of you have looked at quantum mechanical many-particle problems before now? Okay, I know that Lisa and Kathy have done that, right? So this is actually perhaps the Monte Carlo machinery. If you can use that, it's actually, without being too biased, it's perhaps the best money-body method. It's the one which gives you something which is very close to the exact energies. And it has been used in basically all fields of physics and many other disciplines. And the other thing is that the basics of this is what you normally call Markov chain Monte Carlo, or MC squared. And the basic theory is something you can apply to many, many other types of applications. So if you're doing molecular dynamics, for instance, and you have large integrals you need to evaluate, Monte Carlo evaluation is essentially what you end up with. So Monte Carlo methods, Markov chains, stochastic processes are actually the cornerstones of this course. Then we also, obviously, when you do a stochastic calculation, you need to have a proper way of evaluate the results. So that means a statistical analysis becomes important. So this course contains a lot of statistics because that's very relevant for the analysis of the data. So we need also to optimize the convex function. We're going to calculate the energy of a system. You can obviously also calculate other expectation values, but the energy is going to be a central quantity we will look at. And that is essentially a convex optimization problem. Because when you do a Monte Carlo calculation, what you end up doing is actually to optimize a problem in terms of a series of parameters. I will show you the basics pretty soon. And then the second project is a project where we can continue with, let's say, other quantum mechanical systems and use Monte Carlo methods. But then we also have the possibility to switch to other methods than Monte Carlo methods, which I know that some people who come typically from applications of wave function-based methods, either from theoretical physics point of view, applied to condensed matter physics or nuclear physics, or if one comes from quantum chemistry and you're doing atoms and molecules, we have methods like copper cluster theory, Hartree-Fock theory, etc., which is also another possibility for the second project. I'm going to list some of them. So parallelization is going to play an important role. So either GPUs, CPUs, or mix of them is pretty common. Nowadays, the GPU calculation is actually the cornerstone of essentially everything we do. The algorithms for Monte Carlo simulations are pretty important. So we have Metropolis Hastings, something which is called importance sampling, which we're going to discuss. We have methods like stochastic reconfigurations, which is also an important tool, and other methods. These are so-called sampling techniques. And then statistical analysis from Monte Carlo calculations. Some of you have already met Bootstrap. If you took a course in machine learning, you will see that there are many similarities here. But then we have, for the kind of methods we often end up with, there's a resampling method, which is called the blocking method. So resampling is essentially done because the calculations which you end up doing are computationally intensive. So that means that, like in my case, when I do a Monte Carlo calculation, this can take weeks. And that gives me perhaps 1,000 data points. Then, since you're doing a statistical analysis, what you're getting is a mean value, and then you want to assert what the error is, or the standard deviation. Now, since you have a limited sample, you end up often using statistical resampling techniques to get a more precise estimate of the standard deviation and the mean values, or your expectation values. So statistical resampling tools are extremely important when you make large stochastic calculations. And this is something which we will also discuss and which you will implement in your programs. Actually, there was a student some few years ago who improved the proof of the blocking method, and that was an example of something which ended up in a scientific article based on research done in one of the projects here. So for project 2, there are several possibilities. So in project 1, we're going to make life simpler. So we're going to look at a system of weakly interacting bosons. So that means that the total wave function is going to be symmetric. And we avoid what's called the Monte Carlo sign problem and all the problems with the anti-symmetry of the wave function. However, you can include fermions as an extension of project 1. And then we can, what we have to introduce then is an ansatz for the wave function, which contains the anti-symmetry. Now, one of the things which you will see pretty soon when we start looking at the basic elements of Monte Carlo calculations is that we need a trial function. That trial function can be replaced by a neural network. So if somebody is also interested in that, this is a project which many people have worked on, and the results you get are often shockingly good, amazingly good, with just minimal physics. So the neural network is often able to capture. So a neural network replaces your trial wave function. And by giving it essential symmetries of the system, so if the wave function is symmetric, you can bake that in. You have some specific two-particle symmetries, translational invariance, etc., and other symmetries, which you can bake in, and the network is often very, very skillful in finding the right wave function, the right degrees of freedom. So this is one possibility, if you're familiar with machine learning methods. I know that some of you may be interested in copper cluster theory. And there we have the possibility of looking at the standard. This requires actually that you've taken a course in many-body physics and you know something about copper cluster theory. I also have a project on time-dependent Hartree-Fock theory, which combined with specific machine learning methods could actually lead to a scientific article. That's a project which I would like to discuss if you're interested. So project 2 is something which is very much open to your interests. Okay. And then obviously other topics means that if you have other ideas, please don't hesitate to make suggestions. So other topics which we will discuss is actually the optimization algorithms. So there is a focus on algorithms here for doing Monte Carlo methods. And one of the things we often end up with is actually to use a gradient-based method. And many of you are familiar with that from courses in machine learning. And that comes back here. So optimization is a central topic because you're going to have a function which depends on parameters. This function is a convex function, and we are going to look after the minima of this function as a function of the parameters. So it mimics a lot of what many of you have done in machine learning, if you have taken a course in machine learning. So this comes back again, but since we are not going to have that many parameters in project 1, it means that Newton-based methods, Raphson-Newtons or other methods like the Broyden's method, etc., they can actually be used because you don't have so many parameters. Then we are going to also look at it if you're doing copper cluster theory or Hartree-Fock, then you have nonlinear equations. Obviously, object orientation, the codes you will see, the templates we have provided you with in C++ and Python, they are object-oriented. So object orientation is something you will find very useful. Then data analysis and resampling techniques are important to estimate the standard deviation and the error on your data. And then obviously Monte Carlo methods for quantum mechanical many-body systems. And we are going to look at also simulations of 2- and 3-dimensional systems like quantum dots, atoms or molecules, or like in project 1, we are going to look at a model for a Bose-Einstein condensate. And then we're going to look at bosons only. So the wave function will be symmetric, which makes it easier to set up everything. So project one is a simulation of trapped bosons. And this is some of the basics for a chain of Nobel Prizes in physics back in the early 90s till the middle of the 2000 years, the first decade. And in that case, people, what they did was to cool down a gas of bosons to very low temperatures. And there is a phase transition to a Bose-Einstein condensate where all the particles behave like a collective, and they would typically concentrate around one velocity. So the way this works actually is a very interesting technological background. So the trapping of the bosons is done by, and cooling is done by what's called laser cooling. So the trapping is done by setting up electric quadrupole fields. That's a common recipe. And that leads to traps called penning traps and ion traps. So these traps were actually another topic for a Nobel Prize in '89 for the people who developed them. They are, for instance, used in making platforms for quantum computing. They're called ion traps quantum computers, but they're also used for precision mass measurements, because when you have such a trap, then you normally peel off all the electrons, and then you have an ion without electrons. And since this moves around, you know the cyclotron frequency, you know the magnetic field, and then you can do precise mass measurements. So in nuclear physics, this is often used as a way to measure precisely down to 10 to the minus 9 electron volts almost, the mass of a specific nucleus. So the ion traps are, or penning traps, which are variants of these, are extremely important in science. They're used to trap ions. And then if you have a gas of ions, you know that this will have a velocity distribution which follows a Gaussian. By using lasers, then you let photons collide with the ions which have the highest velocities. So their velocity gets reduced by collision with the photons in the lasers. And that means that when you then let them collide, the extremes of the Gaussian distribution collide with photons, the velocities shrink to a sharper and sharper velocity. And at the end, you have all ions marching at the same velocity. And that is gives you a phase transition to Bose-Einstein condensate. So we are going to look at the how to simulate this kind of systems of many interacting bosons in a harmonic oscillator trap. So these ion traps, if you set them up by using electric quadrupole fields, they are harmonic oscillator lookalikes, because they go like the amplitude of the field times x squared plus y squared. And then project 2 can be an extension of project 1 by looking at fermionic systems. These other topics depend on your interests. So I wanted to say a little bit about Monte Carlo and the motivation. So this slide is a little bit dense here, but essentially what we are going to do is to calculate this quantity here. That's the expectation value of the energy. I'm coming back to a more precise definition pretty soon, but now I wanted to give you a kind of motivation. So if you're dealing with the atomic neon, which when you strip away the nuclear degrees of freedom and you only look at the electrons, then you have 10 electrons. 10 electrons in 3 dimensions, which means then that this integral, which you see here, is a 30-dimensional integral. So if you look at this and you think of 10 integration points and you want to use the trapezoidal rule, or if you know more, you would like to use the Gaussian quadrature, for instance, then if you use 10 integration points in each direction, x, y, z, for every particle, that means that you would have, since this is a 30-dimensional integral, you would have to do 10 to the 30, 10 integration points in each direction, 10 to the 30 numerical evaluations. So if you assume then that every evaluation takes the same time, and you have a machine which runs at, let's say, a teraflop, So you can do 10 to the 12th computations per second. You would need 10 to the 18 seconds to calculate that integral, which would give you actually, in a brute force way, a crappy result, because 10 integration points for X, Y, and Z for an atom like the neon atom, where you have the Coulomb interaction, which has an infinite range, that is something which will give you really poor results. You can try that with a helium atom, which is a 6-dimensional integral, which you can do with these methods, and you will see that 10 integration points do not give a very good result. And the lifetime of the universe is estimated to be 10 to the 17th. So this is why you do Monte Carlo sampling. There is also another argument, which I'm not going to go deep into. That is that if you use a traditional method, like the trapezoidal rule, since you now are integrating over multidimensional integral, the trapezoidal rule has an error which scales with your spacing between integration points to some power. So when you increase the dimensionality, the error just blows up because you make a truncation. The trapezoidal rule is just you approximating the function you're integrating with a linear function, with a polynomial of first order. If you use Simpson's rule, you're approximating the function with a second order polynomial. So you get errors in terms of the integration variable, which is called normally the integration step, to a given power. Monte Carlo methods, on the other hand, has an error which scales as 1 over the square root of the number of Monte Carlo samples. And that stays constant. So when you're going into multidimensional integrals, that's where Monte Carlo integration has its strength. So if you're trying to use Monte Carlo methods for low dimensional integrals, there is no way you can compete with Gaussian quadrature. But as soon as you go into, let's say, 10 or higher dimensions, Monte Carlo methods are the methods of choice for evaluating those integrals. So in a certain sense, this course is actually about using Monte Carlo methods for integration. So in a nutshell, if you want to take an overarching view on it. So I'm going to skip some of these. If you think of many-body methods, there's a plethora of these methods, and you may ask yourself, why should I use Monte Carlo methods when you have so many other methods? So I will try to convince you about the benefit of using Monte Carlo methods, but you have a whole set of other methods, and many of you are probably familiar with them. Some of you have taken a course in many-body physics, know that we have methods like large-scale diagonalization, copper cluster theory, which is a favorite method in quantum chemistry. You have perturbative many-body methods, Green's function methods, etc., etc. Now, Monte Carlo methods are normally the methods which are seen as a benchmark for calculating many variables. However, Monte Carlo methods, since they follow the variational principle, they normally target the lowest lying state of the system. So if you want excited states, then normally people would use large-scale diagonalization, but that is limited again by the dimensionality of the system. Yeah?
So that the variational method follows the
variational principle.
Yeah, that it follows from Monte Carlo? Or?
No. So the Monte Carlo method is just an instance of the application of the variational principle. So I will show you that in just a few moments. I will remind you of the variational principle. So methods like large-scale diagonalization, Monte Carlo methods, methods like mean field methods like Hartree-Fock theory, they all follow the variational principle. So the approach which we are going to look at and implement is called variational Monte Carlo. So it's going to give you the lowest energy with that trial wave function. And that trial wave function follows the variational principle. So if you have the exact wave function, and you will see examples today of you having the exact wave function, and that will give you results which obviously are equal to the exact result when you have the exact wave function, because then you're evaluating the integral with the exact wave function. And then you will see how we actually obey the variational principle. This is roughly where we will end the lecture today, so that you will see the link between the variational principle. So the methods target the lowest lying state with a given symmetry. If you want excited states, then you will often have to labor a little bit more and look at other methods. So these methods, so people who work with one specific methods, they will obviously tell you that my method is really the best. And there's nothing which beats my method. So the kind of idea here is to give you the pros and cons of different methods. So when people say they have the best method, be suspicious. So all these methods have their pros and cons. And for those of you who have taken a course in many-body physics, you've seen many of these pros and cons already. If you spend all your life in one of these boxes, definitely you have to justify why you spent your life in one of these boxes. And then clearly you have to claim that what you're doing is the best, right? Always be critical. So I have some kind of, I've been practicing Monte Carlo method for many years. I will try to motivate why this is physically intuitive. And the threshold for getting started, the mathematical threshold, is much lower than other methods. So one of the reasons why we use Monte Carlo methods in this course to solve many-body problems is not only because we want to expose you to Monte Carlo methods in general and all the things which follow, but also because the threshold for getting started is actually much lower. So if you're doing copper cluster theory or Green's function theory, there's a lot of mathematics which you have to go through before you get to the final expressions which are being programmed. Here, if you look at the program which I will show you at the end of the lecture today, it's so simple. You need a good trial wave function, and then you can actually start calculating. And then we have, so the variational Monte Carlo, which we use, is often used as a starting point for diffusion Monte Carlo. And if somebody's interested, that could be a topic for the second project. So diffusion Monte Carlo, you can prove mathematically that that gives you, if you simulate long enough, the exact ground state energy of a system. But normally it needs a good starting point for the iterations. And that's where variational Monte Carlo comes in as an intermediate step. However, the diffusion Monte Carlo for fermionic system suffers for something which is called the Monte Carlo sign problem. So diffusion Monte Carlo, just to explain what it is in few words. Are you familiar with the diffusion equation, roughly? So if you take Schrödinger's equation and you rotate time into complex time, then Schrödinger's equation becomes a diffusion equation in complex time. However, you are then not solving Schrödinger's equation because it's a diffusion equation in complex time, which is not the same as Schrödinger's equation. The spatial part is the same, but the time part is not the same. And that's why you have to simulate for very long times, because in the limit of long complex times, you're approaching the exact ground state result. So this is a kind of benchmark when you do many-body physics. The problem then, when you deal with fermions, is that your probability distribution, which is a wave function, is a distribution of random walkers. Now, when you have fermions, the wave function can change sign. And that leads to something which is called the fermion sign problems in Monte Carlo calculations. This is actually a topic, I mean, this is my bias. If you solve that problem, it's not unlikely that you may meet the Swedish king in December and you get a prize, actually, with a lot of money which follows that prize. However, there's a solution to that, which circumvents the sign problem for fermions. And that is using neural networks with variational Monte Carlo. So that's an option for project 2. So the solution has statistical errors, and they can be large. That's one of the, how to say, the drawbacks of what we're doing. So you need many samples. So essentially, what we are implementing when we do Monte Carlo calculations is Bernoulli's law of large numbers. Are you familiar with that? Okay, I will remind you a little bit later. So this means the more samplings you can do, the better. So you need typically a huge number of random walkers often. So the kind of systems where these methods have been used is essentially all kinds of systems we can think of. And you can just see a list of topics here. Now, one thing which is interesting with these methods compared to, for those of you who are familiar with mean field methods like Hartree-Fock theory, etc., there you often have a single particle wave function or single particle basis as an ansatz. However, when you go to strongly interacting system, that ansatz breaks down and you cannot use it. Monte Carlo methods can actually be used for many, many other types of systems, also strongly interacting ones. But it means that you need to have a good guess for what the trial wave function looks like. The trial wave function is often based on guesses where you have to plug in your physics understanding, but you can find minimal constraints by looking at the Hamiltonian of the system. We are coming back to that. So this is just a list of many, many applications. And if you're doing strong forces like quantum chromodynamics, there's something which is called lattice quantum chromodynamics. So that is quarks and gluons on the lattice. And that is the standard approach for simulating the strong force. So many, many options. So what I'm going to do now is to set up, but I'm going to switch slowly to the whiteboard. And then I'm going to go through some of the basic mathematics here. And then at the end, we are going to look at a very simple simulation, which in a nutshell contains what you're going to do in the course here for the first project. And it also contains an exercise, which defines the beginning of the project, which is just a paper and pencil exercise. Okay, I'm going to switch to the whiteboard. So the starting point is actually this quantity here. And we are going to optimize this, where this T here, which you see, stands for trial. So that's our guess for the wave function. Obviously, if you have the exact wave function, there is no point for us in being here, because then we have solved the problem, right? So we are going to try different trial wave functions, and then we need to find a way to decide if this is a good function or not. But essentially, this is a convex optimization problem, which we are going to try to solve by optimizing parameters included in this function here. Okay? Yeah?
I have to ask, finding a trial wave function,
Yeah.
is pins used for this?
Exactly. So this is what actually people are doing nowadays. So you can actually find a preliminary solution, but normally, so you can, there are several things you can do. If you think of pins, this is physics-informed neural networks, then you're often also interested in the time evolution of the system. If I'm only interested in the static properties, like the ground state, where you have no time evolution, then I would replace this with a neural network, which you would do when you do physics-informed neural networks, where you would bake in information about the boundary conditions, and you would bake in information about symmetries, and then you would let the network find the best representation. There are many subtle things here, which also, if you want to do that in project 2, that is a very nice, many people have done that normally every semester. And the reason for why it is nice is which I think is interesting, because there's a lot of research on what's called explainable AI, which you may have heard of. And when you parameterize something with a neural network, or you try to solve it with a neural network, the network can have millions or billions or zillions of parameters. Now, when you find the optimal solution, the neural network is just defined by a set of optimized parameters. And it's very difficult to extract from that a physics message. What does it mean? Because at the end, what you want is to give people a simple explanation. How do the forces which act on the system, how do they change the system? Why is the wave function looking like this? Why is the system looking like this based on the forces and the laws of motion? This is the kind of message we want to give at the end after a complicated calculation. And many of the standard methods like Hartree-Fock theory, mean field theories like density functional theories, etc., they have baked in a lot of intuition about the systems. And you can make interpretations which are easy. When you do Monte Carlo methods with a trial wave function well-defined without neural networks, you can do that. But with a neural network, it's very difficult to extract it. So there is a lot of research going on finding out what the parameters of the network mean. Now, when you do neural networks, some of you may have heard about the barren plateaus. I don't know if that rings a bell. So that typically means that some of the parameters may have a gradient which goes to zero during the training. And people have shown through research now that some of these gradients which go to zero are coupled to parameters which are physically irrelevant. So think of FCI. If I diagonalize a matrix of a 1 million times a 1 million, maybe the state you're looking after is dominated by 10 of these 1 million states. The rest is just random chaos. So when you do an FCI calculation, you can extract immediately a simple message. This is the structure of the state in these and these terms. And this is what people are trying to extract from neural networks. And that makes it much more interesting if you can extract some meaningful physics message from a complex optimization problem. So that's what, at the end, even if we are ramping up lots of fancy methods to solve the problem, at the end, we want to extract a simple message. What are the driving mechanisms behind the physics you're seeing? So we should never lose sight of that, even when we are deep into heavy calculations or numerical simulations.
You call the methods for finding the important parameters.
So one method which is widely used is called the full configuration interaction theory, which means that you set up a problem with a Hamiltonian, and you have what's called a Hamiltonian matrix, and you diagonalize in a basis. And when you diagonalize, then you have the coefficients in front of the linear expansion of wave functions, and some of the coefficients are basically zero. And that tells you that these and these states are less important. We can come back to that. Okay, went a little bit over time, but let's do 15 minutes break. You can grab coffee at the CCSE if you want to, etc., etc. And then we just begin at 20 past the hour, if that's okay. Okay. Okay, so what we're going to do now is to set up the basics. And you will be surprised to see how simple the equations are. And I want to link that with the first thing we are going to do in the project, which is a harmonic oscillator in one dimension with one particle. And then we are not going to look at the beginning when we develop the project at the interactions between the bosons, but we're just going to have a non-interacting system. And then we have the exact wave function, which is a harmonic oscillator. And the harmonic oscillator with one particle, two particles, three particles, etc., 1, 2, and 3 dimensions. We have analytical answers for that. And since the particles don't interact, the energy is just the sum of the individual single particles. So if you have one particle in one dimension in the lowest lying harmonic oscillator state, the energy is 1/2 times the oscillator frequency times h bar. If you have two particles, it's 1/2 plus 1/2 times this oscillator frequency, so it's 1. if you have 3, etc., etc. So the energy is then very simple to compute. And we are going to see now how we can set this up, because this will be a benchmark for you when you develop the program. The non-interacting case, if your code is running correctly for the non-interacting case, which is what we will work on till the very end, and then we plug in the interaction. Because if everything functions for the non-interacting case, it's very unlikely that it will not function when you plug in the interaction. Okay? So the basic elements we're going to look at now are those which you will apply again and again in the project. And the basic elements are pretty simple. So so what we're going to do now is in the Monte Carlo machinery, we are going to define this trial wave function. So W and F is wave function, that's my acronym. And we are going to define that as a C of t. And this will be a function which in principle will depend on various variables, and I'm going to set them up. And I have this variable theta. So I'm writing them as vectors. So R is the collective coordinate for the positions of all the particles. So we have R1. So this is my attempt to write the letter R. And as some of you know, I mean, this is one of the letters I always struggle with since I was a small kid. Actually, in elementary school, I still remember with quite some mixed feelings. I was set down to write the letter R for several minutes and fill in pages after pages. And I still couldn't write it correctly. But this is my best attempt at the letter R. And then these are the spins. So these are the collective positions for the particles. And these are the spins of the particles. And for the boson case, we are going to simplify life because we are not going to have a spin system. So we're going to have a zero spin particle. So we're not going to look at spin as a degree of freedom. Actually, the Hamiltonian, which we will look at, does not act on spin. So that simplifies things. But normally we will have a collective variable, which I call for X, which is just then the collection of R and S. So these are the objects which define the wave function. And then we have a theta, which are just the parameters. And we are going to call them variational parameters. So we will have a set of parameters. And in the first project, we're just going to have one parameter, which makes the whole optimization very easy. Because we don't need to calculate a gradient, we just need to have the derivative of the expectation value of the energy. And that's the quantity we will optimize. So here we will have different variables, theta 1, theta 2, etc., up to some theta of m. So the letter n, which you see here, this one here, and also this one here, that's the number of particles. So I'm going to use that one. N is the number of particles. So we're going to have a function which is defined by these different parameters. And that means that the energy, unless we have the exact energy, is going to be a functional of this wave function. So the energy, I'm going to define this as a functional of theta. And that is going to be given by an integral where I now sum over the spins and I integrate over all the coordinates. And then I have psi of t. And then this depends on R and S and theta. We have a Hamiltonian here, which depends only on R and S, but in principle, so this is just the full dependence. And we have R and S and theta. And this is divided by a sum over S and d of R and psi of t. And I'm just going to write it like this, of R S and theta here, square. This is the standard quantum mechanical variables here. Now, one thing which we often will do is to simplify this summation here. So if we write this S here and then the integral over d of r, we will simply rewrite that one in terms of this d of x. Okay. So that means a summation and an integration. But that's a typical compact notation which we often end up using. And also let me just write this d of r. This is the same as d of r1, d of r2, etc., up to the final particle. So it is a multidimensional integral which we are evaluating. This is the starting point. Then, since we want to do statistics, we are going to rewrite this one in terms of something which looks like a probability times a variable. And this is the calculation which we are going to set up now. But let's just quickly move on to the thing we want to do. So we are going to define a function we are going to optimize. And we want to find the optimal parameters. And this optimal parameter is given by a theta hat. And this is the same as taking because the energy, and I'm not going to prove that, is a convex function. So we have a minimization problem. And this theta now lives in this space. So it's a complex space. They can be complex variables or they could be real variables. Normally, we will use real variables, but I'm going to put that as a complex variable in the space of m parameters. And we are going to evaluate this optimize this quantity here. No, not hat, sorry. So what that means in practice is that we are going to take the gradient with respect to theta of E theta. And we want that to be 0. Okay? So suppose now that theta, we just have one parameter, okay? Assume only one theta. One theta. So we are looking at a scalar, but in principle, this can be a function which depends on many variables theta. And if you're doing a neural network, for those of you who are familiar with that, then we will have millions of parameters, or even more, depending on the size of the network. So what this means is that in practice, if we now have only one parameter, is that what we are going to evaluate by Monte Carlo calculations is the following. So we are going to have a trial wave function. We are going to calculate the energy for different values theta. And our energy may look like this. So there will be an ideal point. Now, what I'm going to set up here, this is the Holy Grail. This is the exact energy. And I'm going to call that one for E0. This is the lowest state for that specific Hamiltonian. So the Monte Carlo method is actually targeting, due to the variational principle, the lowest line state. So this could be the results we would get with, suppose, a trial function 1. And that means that the optimal parameter is this one. And I'm going to call this energy here for E1. But then somebody could now give me another function. Now, let me just change the color. So suppose now I have this function. And that gives me a slightly different minimum. So I could have psi of T2. And that would give me an E2 here. And then perhaps I have another parameter. So we could call this 1, and this will be theta 2. So clearly, if you now are going to make an evaluation of the results, you would say that this T2 function is the preferred one, because that brings us closer to the exact value. So different trial functions will give us different energy minima, because we don't have the exact wave function. If you have the exact wave function, then obviously you get the exact energy. And you will see that in just a few moments with some simple method, yeah?
I'm sorry, but how do we get 0 if we don't have an exact solution?
So in the first project, when we do the non-interacting case, we know that the lowest energy is the exact harmonic oscillator energy. But in most cases, you have no idea. So what happens then, if I give you a Hamiltonian in a given system, what you would typically do then is to try different trial wave functions. And depending on the complexity of the problem, at some stage you would have to stop. And you would say, I'm happy with this trial wave function. This is the closest I get by looking at the minima. Because when you look at the results here, you see now that, okay, if E2 is lower than E1, then you would obviously pick E2 as a better approximation. If you now make a new one and you find a lower energy, so if I give you 10 trial wave function, you would pick the one which has the lowest energy. And you will say, this is probably closer to the exact value. But unless you know the exact value, you would just have to try different test functions. And that's why analytical results are so important. And the harmonic oscillator with no interaction for as many particles as you want has an analytical answer. And that means that if our code reproduces that, we know that the code is functioning most likely correctly, and then we can add more complications to it. So that's roughly the basic philosophy when you deal with Monte Carlo methods. So let me just quickly remind you of the variational theorem. So the variational theorem states, suppose now that I have a Hamiltonian which acts on a state, and I use this standard Dirac notation, and this is the exact eigenstate and the exact eigenvalue. And these states, which we have here, if we look at the norm here, they are assumed to be orthogonal and normalized. So that means that when I take the overlap between the states, I should get a delta ij. Are you all familiar? I guess you're all familiar with the Dirac notation here. Good. So with that, when you have a complete basis, so this basis of size is a complete basis, then I can always define a new function, which is a linear combination. And in principle, this basis is an infinite basis. But you will always make a truncation. But so I'm not going to put the limits. But in principle, the basis I have is an infinite basis. I have an infinite Hilbert space. So then I have a C of I, and then psi of I. And then I know that if I calculate the energy, and now the energy is a functional of this state phi, this is the same as us calculating this quantity here. And since I don't have the, I haven't normalized this state, I need to normalize it here, okay? This is nothing but the integral which I wrote in the previous, on the previous slide. So if you look at this expression here, this is nothing but the one which we have here, where here we're actually writing everything out in full detail. And the trial wave function here could be this function phi, which I put up. Now, if you look at this equation here, then we know that when we plug this in, this becomes equal to a sum over I and j. Then I have a Ci complex, Cj, and then I have my psi of I. and then my psi of j. And due to the orthogonality, then this denominator reduces to a ci squared. And also we have that the sum over the ci squares, since we are assuming that this is an orthogonal and normalized basis, that has to sum to 1. So the denominator sums to 1. And then we know that this quantity which you have here, this one, this is just simply the delta ij multiplied with E of I. Because these states which you have here are eigenstates of H. Okay? So that means that what I can write out then is that E of I is equal to the sum of I of C of I squared multiplied with E of I. Is that what I called it? No, I called it lambda. Sorry, lambda, I had lambda. I should correct that now. So this is lambda of I. And then I should correct this one, lambda of I. And we know that this one, unless the coefficients are equal to 0 for all except I equal to 0, then we know that this quantity here has to be larger than E0, unless all CI's squared are 0 except CI 0. Because then lambda 0 is equal to E0. So if the coefficients, if the exact wave function or this phi is equal to the exact wave function for E0, then this relation here, since the CI's are always larger than or equal to 0, and we're also assuming that E0 is sorry. So E0 is actually, messing up things here, is equal to this lambda 0, which then is like this. So this is just a variational principle. So unless we have the exact wave function, then we will always get an energy which is larger than the exact energy. So this is essentially the variational principle. Now, what we want now is something which allows us to rewrite this integral as a probability times something. So in order to implement Monte Carlo methods, I want to rewrite everything as a probability. So to use Monte Carlo methods, MC methods, we would like to evaluate, we want to evaluate or would like to evaluate something which goes like something which looks like and now I'm setting up the expectation value of a variable. So this is the moment of a variable X. So X can be any type of variable. It could be the energy. And this N is just the moment. So it could be X to the power of 1, which is the mean value, X to the power of 2, X to the power of 3, etc. And we want to have this one to be given in the form of a probability, P of X, multiplied with X of N of D of X. Now I'm assuming that this is a one-dimensional probability, just for simplicity. If this is a discrete probability, we would like to have this one to look like a P of X of I of x of I to the power of n. And we know that the mean value, just to remind you of some of the basic statistics. So with the mean value is mu of x, which is just the expectation value of x, which we often write in this physics way, like with this kind of brackets. And that is simply the probability of P of x of d of x. And then we have the variance. I guess this, I hope you don't get offended if I repeat some of these basic statistics equations. We have the variance, which is just the expectation value of x squared minus the mean value squared. So if you look at the variance of x, which we often will also write like sigma x squared, this is nothing but the integral over P of x, and then we have d of x, and then we have x minus the mean value squared. And we know that this is something which we can write out as the expectation value of x squared minus mu of x squared. Or if you prefer this notation, it's x squared minus x squared. So these are just different notations. And we know that the standard deviation, STD, is given by sigma x. Now, in our case, we often don't have the probability distribution, so we will use the sample mean value. But we are coming back to that a little bit later. So what we want to then is to have something which looks like this expression here. But if you look back at Schrödinger's equation and for the wave function and also the expectation value of the energy, it doesn't look like this. So what we do then is the following. So we're going to define the probability distribution. It's a PDF. That stands for probability distribution function. And we are going to define that one to be equal to the quantum mechanical distribution. So we have a psi of t of x, and then these variational parameters divided by the norm. So this is actually the quantum mechanical definition of a distribution based on the wave function. Okay. So this is nothing but using Born's ansatz about what the wave function means in terms of a probability. So the probability of being in a position x with these parameters theta is given by the wave function squared divided by the norm of the wave function. Okay. Now, if I go back to this expectation value of the energy as a function of this theta, and now I'm going to write this one in a little bit more compact way. So I'm going to skip the variables here. So what we have is a Hamiltonian acting on psi of t divided by the integral of psi of t squared. So I hope you can excuse me because I'm not going to carry with me all these different variables. Now, what I'm going to do now is simply to introduce a new quantity by multiplying with psi of t and divide by psi of t. And you see now that if I multiply with psi of t here, then I get something which looks like this. And I have this in the denominator. So what I need to define next is a new quantity, which I'm going to call the local energy. And you can actually prove that even if the wave function goes to zero, this quantity is, because you're multiplying with the probability there, this is a quantity which is non-zero, or it doesn't diverge. So I'm going to define something which I will call the local energy, which is a function of x and the variational parameters or the parameters. And this is simply 1 divided by psi of t of x of theta multiplied with the Hamiltonian, which depends only on x, and multiplied with psi of t of x of theta. So this is going to be my local energy. And if I plug in this quantity, then I can actually rewrite E of theta as an integral over dRx of this probability. So I'm going to call this function here for my probability of x and theta. Sorry, I forgot to put that one. So this is going to be given by the probability x of theta multiplied with this local energy, which depends on x and theta, like that. And that looks like an expectation value. So this is just us rewriting Schrödinger's equation. Now, the fact that I have defined this probability is going to be important later when we introduce something which is called importance sampling, because then we are going to pick the points x according to the probability which we want to simulate. And that means that you will pick x's which are relevant and which give you a probability and wave function which is non-zero. Because if you can pick x values where this probability is 0. And if you have, let's say, 50% of your stochastic samples give zeros, then you will be wasting a lot of CPU cycles. And you will see that in the beginning, we are just going to do a brute force integration where we just pick points randomly without thinking of how they are distributed according to the probability. So that leads to what's called importance sampling and a modification of the Metropolis algorithm to something which is called Metropolis Hastings, which we are going to implement later. And that's going to give us a better way to evaluate integrals. Now, there's one thing which I'm going to prove next week, which I'm anticipating now, is that this result here is something which we will write out like 1 over the number of Monte Carlo cycles. M is a number, and then there's the Monte Carlo cycles. And this is a summation from I equal 1 up to the number of Monte Carlo cycles. And we are going to calculate E of L for these positions of x of I. And x of I is a configuration because that's where the particles are placed and which spin values they have. So each x of I is one possible configuration which we will pick randomly. Now, this is the approximation to the integral here, where we now are going to use Bernoulli's law of large numbers. So this is called a sample mean value. And the hope is that when this MCS goes to infinity, that we actually are approaching the mean value which you would get if you had the exact distribution. So keep in mind now that you have 1, the exact mean value. If you go back to the equation which you have here, like the one down here, or this expectation value, this is something which you can calculate if you know this one. In principle, we don't know the exact probability. So that means that the mean value is normally approximated by the sample mean. So you have a sample of observations, and then you calculate the mean value over that. What you're saying then, if you now look at the factor 1 over m, which you have here, is that every possibility has the same probability of being implemented. So that means that every sample, if you have 1,000 samples, everyone has a probability 1 divided by 1,000 of being picked. Now, you can show through Bernoulli's law of large numbers that this quantity, when MCS goes to infinity, is going to approach the exact mean value. We are coming back to that. But this is what we are going to do in practice when we do the simulations. So next week, we will discuss the Metropolis algorithm and how this is actually done. Today, we are just going to implement it. And we are going to look at an example which is relevant for the project. So I also wanted to give you a question here. There is an interesting quantity. So the variance of the Hamiltonian, which we have, is given by, so suppose now that, so let me just put it down here. So suppose now that we are looking at the ground state of the system, and this is E0 times psi 0. So this is the state we are targeting. And formally, the definition of that one is given by, if we're now using the definition of the variance, this is the Hamiltonian squared divided by psi 0, and we're assuming that this is normalized, so the denominators are equal to 1, minus, and then I have psi 0 okay. This is the formal definition of the variance. If I have the exact function here, can you, without doing any calculations, say what the result should be? You can actually do that. If I have the exact function, I know what the variance is. And it's a number which just a few years ago was equal to the number of points which Norway would typically get when they try to qualify for the World Cup. 0. So this is actually equal to 0 if you have the exact function. Because you know that when this one acts on this state here, so let's just do that properly. So this gives me just E0 squared. This is the same as E0 because the denominator is equal to 1. This is equal to 1. It's a orthogonal and normalized basis, which we have. So what I have is E0 squared minus E0 squared. And you will see in the example, which I'm going to show you now, when I have the exact wave function, that I'm actually going to get a variance numerically, which is equal to 0 with a Monte Carlo method. So that's an extremely useful test. And you will see that when you're going to develop your program now, that you're going to get a 0 variance when you have the exact wave function. So for the harmonic oscillator with no interactions, you should get, for the optimal parameter theta, you should get a variance which is exactly equal to 0. So this is also something when people have performed the variational optimization, is that they have both varied the variance and the energy. So you can tune the variance and the energy to see if you get a better approximation to the energy. Because the variance is something you know. You don't know the exact energy, but you know that if you have the exact wave function, then the variance should be 0. So when you're going back to, let's now say that somebody gives you these 2 trial functions. And then you see that one gives a lower energy. What you will also see is that the one which gives you the lower energy also has a smaller variance. So if you don't know anything and you're asked to pick a function, you would always pick the one which gives the lowest variance or the one closest to 0. So we do have an exact result. Now, the problem why you don't do an optimization of the variance instead of the energy, because you could say now, why don't I make my optimization not of the energy, but of the variance? The problem is that if you want to do that, if you want to optimize the variance, you have to calculate the gradient of the variance, and that will give you many Monte Carlo integrals to evaluate. And that's simply a numerical issue. If I calculate the gradient of the energy, I'm going to get 3 integrals to evaluate when I optimize it. If I do the variance, I have more integrals, and it's simply an additional complication. Okay, so one thing which I'm going to do now, since we are going to move into the lab session afterwards, I'm going to show you in the next session how we can get started with a Monte Carlo calculation and what kind of ingredients you need to get started with a project. So the lecture will stop here, but I will also record parts of the next session, which is roughly 20 minutes, because then I'm going to show you how to get started with a project and what you need to do specifically. So the first part is actually paper and pencil, and then you can look at the program which I have and see if you can make a similar program yourself. Does that sound okay? Because after the break now, we are going to look at the simpler case, and we are going to look at the one-dimensional. So let me just put it up before we stop here. So we're going to look at the 1-dim harmonic oscillator. So the problem which we have then is given by this differential equation divided by 2m of d dx, and then we have some psi of x plus 1/2 of k times x squared times psi of x, and this is equal to an energy E of phi of x. Now, I'm going to give you the exact answer. So the exact answer for the ground state, so phi 0, so when I put a 0 subscript, that is the lowest lying state. This is given by a normalization constant times E multiplied with -1/2, and then there is a parameter which I'm going to label alpha of x squared. This alpha is equal to 1 for the exact solution. But we are going to treat this alpha as a variational parameter. And we're going to vary alpha. So we're going to have this parameter theta, which we discussed earlier, is now going to go over to just a single parameter alpha. The exact solution is given by some normalization factor times e to the -1/2 times x squared. I'm going to put h bar equal to the frequency, equal to the mass, equal to the charge, equal to 1 to simplify. So I'm going to use natural constants. So that means that the energy, E0, actually I should write this E of n, because it's quantized of the harmonic oscillator, is going to be given by n plus 1/2. In principle, there should have been an h times omega here. So these parameters, h and omega, they are actually baked into this parameter alpha. I'm coming back to that a little bit later. But we are going to look at dimensionless quantities. And that means that if we want to have the dimensions of energy, we would have to multiply with these constants. So the way we are going to set up the program is to simply run everything in dimensionless units. And that means that in this specific case, x has no dimension. If we want to have a dimension length, we would have to multiply with the appropriate constants. So let's just keep it like this now. And this is going to be our trial wave function. So after the break, I'm going to show you how you can set up the calculations for Monte Carlo calculation. And I'm going to show you the results of the calculation with a Monte Carlo code. And this is roughly to get you started with the project. Does that sound okay? So after the break, I will sneak in some more calculations so we can actually get started. And next week, we will go through the Metropolis algorithm and the statistics background, which is needed to understand, for instance, why we can do what we have here and how we are going to do it. So now I'm just going to throw you into deep waters and hopefully we can pull you back pretty soon. We can do with that. So when we are going to run a calculation now for this, what we need to do is to first calculate the local energy with the harmonic oscillator. So the local energy, if we look at that one, for this specific case, so the quantity which we need to set up first is the local energy. And now it's going to be a function of this parameter x, so just one dimension. There is no spin, so x is just the position. And then we label the parameter alpha instead of theta. So this is our variational parameter. Now what we need to do then is simply to calculate the following quantity. So we are going to have 1 divided by psi of t as a function of x and alpha. And then we have the Hamiltonian here acting on psi of t. And psi of t of x and alpha is equal to, and we are skipping the normalization constant. This is something I will come back to later, which is a nice feature of the metropolis sampling, is that the metropolis sampling looks at ratios between the wave functions. And then the normalization constant, which is actually one of the nasty objects, because you have to integrate over a multidimensional integral. We don't need to do that. So we are just going to skip the parameter, and we are simply going to use a trial wave function, which looks like this. So we know that the harmonic oscillator, the exact one, the exact result, is the case when alpha is equal to 1. So what we need to do then is simply to calculate minus, and then we have 1/2 d of x plus 1/2 times x squared multiplied with psi of t. And then we have to divide by psi of t. So I'm going to give you the answer, but it's okay to do it yourself, because when you have more particles, one can easily forget some variables. For one particle, what you get then when you plug this in is that the local energy. So I want you to do that as a first exercise, just to make sure that we are on the same wavelength. So we have an alpha squared plus x squared of 1 minus alpha to the power of 4, like this. I can then calculate the integral. So this can be calculated analytically, as we know. So with the harmonic oscillator, so we would need, so if we're now looking at the energy, the expectation value of the energy as a function of alpha, that is now going to be an integral over d of x, and then we have the quantum mechanical probability of x of alpha, and then we have to multiply this with E of L of x of alpha. So that integral can be calculated analytically. So we just need to plug in the harmonic oscillator. So if you calculate that integral analytically, so I'm just going to give you the answer. So feel free to check that that's the way it should be. So what I will get then is the following. So the answer is going to be 1/4 of alpha squared plus 1 over alpha to the power of 2. So this is the energy as a function of this problem. This is the expectation value of the energy. So when I go back here, when I take the local energy, I plug in the probability, which is now just this wave function here squared, divided by an integral. So everything can be done analytically. Then I get this as the final expectation value of the energy. Now, when I do the optimization, then I have a d of d alpha of E alpha. This is my gradient, but since I only have one variable, this reduces to this simple expression, which we want to evaluate. And if I do that, then by taking the derivatives with respect to alpha, that tells me simply that the best result for alpha is the one when alpha is equal to 1. And you see now that if I plug in alpha equal to 1, then E of alpha and alpha equal to 1 is simply 1/2. And if I go back to this expression which I had, E of n, which in this unitless expression was given by n plus 1/2, and then you put n equals 0, then you see that the exact answer, E0, is equal to 1/2. Now, you can get